start recording. So here we have a maximum, and here we have a maximum. So that's Mount Everest. This is, I don't know, some foothill right here. Then we have two relative minima, which is 2 points right here. And these points are turning points where we go from increasing to decreasing. So now, guys, it's up to you, 50 questions like this on a test, to tell me, where is this graph increasing? Over which intervals? And there are 3 parts of orange, so you have to give me 3 parts of increasing. Who wants to try? And again, you have to look at the x values. We do not care about the y values. Where is this graph increasing? Increasing starts right here. Even so, the arrow is pointing down, the graph is still going up. So, who wants to try? Not all at once. Come on. Negative infinity is good because x values, this would keep going and going. And where does it stop?
1.
It stops at 1. Where else is it increasing? From 2 to
4.
Yes, from 2 to 4. Where else is it increasing?
6.
From 6 to infinity. You got it. There you go. Okay, where's the graph decreasing? 1 to 2. And from 4 to 6. Beautiful. Yep, that's it. Increasing, decreasing over x values. Don't use 7, the y values. Okay, more graphs from the book. Let's take a look at this beautiful number 12. You don't see the number, but I'm writing it down. This is a beautiful upside down parabola. Where's the graph increasing? Increasing would be right here where it's blue. So from negative infinity to 2.
And then decreasing from 2 to negative?
No, to infinity. You're looking at the x values. X is positive right here. Cool. I like it. Let's take a look at number 14. Let me ask you a bunch of questions. Number 14, is this a function?
Yes.
What is the domain?
Negative infinity to positive infinity.
What is the range? Negative infinity to positive infinity. What is f of 4? Look at all. I can ask you 20 questions with one graph. If you get one wrong, you get them all wrong. Okay, where is this graph increasing? Increasing. Is it increasing? Does my pen go up? My pen does not go up. So it's not increasing whatsoever. Where is it decreasing? No, it's not everywhere. There's a flat line in between. So where's it decreasing from? Negative infinity to negative 1, and from 4 to infinity. X values. X values are positive over here. Don't look at the y values. Where is this graph constant? From negative 1 to 4. Beautiful. Now, if you look at number 15, when we're talking about the relative minimum and maximum, we're usually looking at the y value. But I'm going to just tell you, just give me the ordered pair. If you look at number 15, where do we have a relative maximum? What are the ordered pairs?
-1, 3, and 4, 3.
-3, 4, number 15. A relative maximum would be here and there. So -3, 4, and 2, 5. At x equals 2, we have a relative maximum at 5. That would be the proper way to say it, but you can just tell me what the ordered pair is. What's my relative minimum? Relative minimum? Hello?
-1/2, -2.
Somebody say something. Yes. Yes. Now, let me ask you for number 15. How many turning points do we have?
3.
3. Now remember that. Next week, I ask you what the degree of this polynomial is. If we have 3 turning points, the degree of this polynomial is 4. Because it's always one more than the amount of turning points. That's for chapter 3. Okay, even and odd functions. Got to talk about those. An even function is symmetric with respect to the what? To the y-axis. So our most famous even function is the parabola. And I'm just going to sketch it here. The parabola is symmetric with respect to the y-axis. And another easy way, so the parabola is f of x equals x squared, the square function. The parabola is an even function. And of course, an easy way to see if we have an even function is, look at the exponents. If all exponents are even, then you have an even function. Simple as that. Algebraically, you have to test for that. If f of x is equal to f of negative x, then we know the function's even and is symmetric with respect to the y-axis. For example, if you pick -2, you get 4. And if you pick +2, you also get 4. -2, 4, and +2, 4. So f of x is equal to f of negative x, which in this case is a +4. Let me give you an example and show you algebraically what I'm talking about. F of x equals x to the 4th plus 2x squared. You don't even have to do anything. You know it's even. You see the even exponents. But we need to test f of negative x. If both of them are the same, then we know it's even. So what do you have to do? You have to make your x's negative x to the 4th power plus 2 times negative x to the 2nd power. You're replacing the x's with a negative x. If you simplify this, negative x to the 4th power, then you get a positive x to the 4th plus 2x squared. So here you go. We know they are the same, so this is even. F of x is x squared plus 3x. That would be what? Neither. Why is that neither? Because you have an even and an odd exponent. If you have both of them in one function, then that's considered neither. So what do you think is an odd function? Ow, I can't sit here anymore. Odd function.
Symmetrical across the x-axis.
Nope. The most famous of the odd functions is which one? Well, this one here that says f of x is raised to what power? To the third power. If you have an odd exponent, odd functions are symmetric with respect to what? The origin. I can't say it anymore. It's too late to say origin. Here you go. So what does that mean? F of x is equal to negative f of negative x. If we have a 2, then my y value would be 8. 2 times 2 times 2 times 2. If we have a negative 2, my y value is negative 8. Negative 2, negative 8. So the x is being made negative as well as the y value has the opposite sign. And they are symmetric with respect to the origin, which is, of course, 0, 0. So if you have a combination of odd and even, then it's neither. But let me ask you, now, if something is odd, it has to go through the origin. No, let me not ask you tonight because we haven't done that yet. But real quick, f of x equals 16x to the 5th plus 12x to the 3rd plus 2x, odd, even, or neither? Yeah, it's really that simple. Even at 8:30 in the evening. Now what I'm going to skip over, because I need you to have a fresh mind and thinking about that, is the difference quotient. We're going to do that Thursday first thing, but we're going to go into 2.6. I want to ask you something else. Oh, look at this graph here. Odd, even, or neither? Odd. Right. There was something I wanted. What's 35? I wanted to do something. F of x is 5x to the 3rd minus 3x. This is out of the book number 37. Odd, even, or neither? Let me actually show you this real quick and algebraically, not just by looking at it, if that's really odd. I got to do it once. The first step is we're replacing the x with negative x. My pen doesn't want to write anymore. 5 times negative x to the 3rd power minus 3 times what? Negative x. If we simplify that, something negative raised to an odd power that's still negative. So simplified would be negative 5x to the 3rd plus 3x. Right? Yes? Everybody seems really awake. You see that these two are not the same. Not the same. That means they're definitely not even. Okay. Now we're going to throw a negative in front of it. Negative f of negative x, negative 5x to the third plus 3x. And simplify that. That's how you test algebraically if something's odd, even, or neither. So you distribute the negative, you get a positive 5x to the third minus 3x. Is that the same as the original one? Yes, so that makes it odd. Not same means not even. Same means odd. Here you go. Okay, and I give you one more because I see you like it really a lot. Actually, I'm making this one up. G of x is 2x to the third plus 4x right now without going through the algebra, odd, even, or neither. Right now it's odd. If I change it, is it still odd? Even? Or neither? The plus 1 makes it lift up 1 unit. Now it's not going through the origin anymore. Oh. However, if I add a plus 1 to a square, it's still symmetric. We talk about this on Thursday. Okay, so that's most of 2.5 done. Like I said, I want to do difference quotient on Thursday. 2.6 is basically 2.6 on graphing. So we're going to graph the parent function. We're going to look at them. We're going to graph piecewise function, and then we go home. Because that's what 2.6 is all about. Then on Thursday, I have to do 2.7, 2.8, and 2.9. Okay, library of functions. I call them the parent functions. Linear functions, square root, cube root. I'm going piecewise functions. We're going to graph an absolute value. Why not? We'll also know the square function, the parabola, and those are all the square root, cube root, parabola. These are all the functions we're going to talk about. Now, they start off with 2.6 about y equals mx plus b. I don't want to talk about y equals mx plus b. I don't want to go into the slope, and I just want to tell you that a linear function is now f of x equals mx plus b. Instead of y equals mx plus b, we have f of x is mx plus b. If m is equal to 0, what do we have left? B. So if m of x is equal to 0, we get f of x equals b. Now, besides Ben's not going to say it. What kind of function is f of x equals b? If I were to graph that, for example, if I were to ask you f of x equals 5, how would you graph that? F of x equals 5 is, somebody said it, a horizontal line. Y equals 5 is a horizontal line. The slope is 0, remember? No. So f of x equals b is called a constant function. Constant function. F of x equals x, where y is equal to x, looks like so, is called the identity function. Constant function, identity function. And you have these pictures in the book with positive slope and negative slope. I don't want to talk about slope. The next one I want to graph, that's the book graphed. Actually, I'm going to go out of order. I'm not going to graph this one. I want to graph something we haven't graphed, so let's talk about the absolute value function. Absolute. That is one of the 6 parent functions that you need to know how to graph. Let me make a t-table. -3, -2, -1, 0, 1, 2, and 3. The absolute value in symbols looks like so, the absolute value function. Let's graph one. If x is -3, what is y? 2, 1, 0, 1, 2, and 3. One, 2, 3. -3, 3, -2, 2, 0, 0, 1, 2, and 3. So an absolute value is always easy to recognize. Why? We already talked about this. It looks like a V. It has a pointy tip. Every time you see a V, you know it's an absolute value. What do you know about the domain of an absolute value?
Negative to positive infinity.
Is it the square root function? No. Is it what are you drinking? Proline. Handshake, okay. It's also not a rational function, so it must be negative infinity to infinity. What's the range? What is the range? Say it loud, David, say it loud. 0 to infinity. I heard it. 0 is included to infinity. That's an absolute value function. What else do we want to graph? The square root function? Let me change my background. Here you go. Now you're all awake. Or not. Go ahead and graph the square root function. Make a t-table. Start at -1, 0, 1, 4, and 9 for the x values. The symbol for square root function, square root of x. Go ahead, graph it. Do something. Wake up. Bless you. Bless you. So if x is -1, what is y? It's Narnia. And I we cannot graph. Even so, when you go into higher level math, the x-y coordinate system is changed into the AB coordinate system, then you can graph it again. What's the square root of 0? Square root of 1? 4? 9? 3. Okay. So we start at 0. -1 is not a real number. This is a real number coordinate system. 1, 1, 4, 2, 9, 3. Somewhat like this, like so. I missed the mark there. Okay, next. The most important of them all, the book calls it the squaring function. I call it the parabola. F of x equals x squared. And now I can use my parabola. Beautiful it is. What color do we want? Blue, why not? Starts at 0. You can make it T. And, pressure's on. Let's see if I can. Oh, look at that. Look at this. Eee. Oh, most beautiful. Why is there a dot here? Nobody knows. Okay. What's the domain of a parabola? If I call you at 2 a.m. in the morning and I ask you what the domain of a parabola is, this has to come quick, really quick. -infinity to infinity. What's the range? The parabola is very similar to the absolute value, but we have curvy action going on instead of a pointy tip. Because the parabola, the absolute value really comes from positive x and negative x. Anyway, beautiful parabola. Where's the parabola increasing? 0 to infinity. Where's it decreasing? Do we have a relative maximum or minimum? Where is that minimum? Right. You guys having way too much fun. Okay, square function. One more. Why not? We got time. I could do all of 2.7 still this evening. I could do watch this, doing 2.7. You think I'm joking? Look at this. Now, my blue graph is the parent. My red graph is the child. The shape is still the same, I just moved it down. So this is all 2.7. We're moving up, we're moving down, we're moving... Oh, look at this. I just want to use my parabola, that's why. Watch this. This parabola can go to the left or to the right. How about the parabola that is reflected? All goes back to the blue one. Okay, it's getting late. I'm losing my mind. Here you go. With my little parabola thing. I can have a parabola. Now I'm having issues. I can shrink it and stretch it. But that's for Thursday. Okay, we got to graph one more. Cube root. The cube root function f of x equals the cube root of x. How does it look like? Maybe we can get one piecewise function then. Let's do x, y, negative 8, negative 1, 0, 1, and 8. Why did I pick these values? Because I did. The cube root of negative 8 is what? Negative 2. The cube root of negative 1 is? The cube root of 0? The cube root of 1 is? And the cube root of 8 is 2. Here you go. A cube root looks like so. Like a snake kind of type. What is the domain of a cube root? What's the range of a cube root? No, the range, this one keeps going and this keeps going. Yep, the range and the domain are the same. Yes?
Does the odd and even function rules apply to cube roots and like even roots?
It applies to, the odd one applies to the cube root. and the cube, but not the square root. The square root is not even with the square. But with the cube roots, you're right. Yes. Speaking of, I'm just going to sketch it. I'm not going to make, because I sketched it already. The cube function, how's the book called? Cubing function. The cubing function. I'm not going to make a t-table. I'm just going to sketch it. The cube function is the inverse, which is 2.9, is the inverse of a cube root. Now, the domain of a cube function is also negative infinity to infinity, and so is the range. Okay, now we're going to graph one more and then we go home. And then, actually, we're almost done with 2.6, too. I want to graph a piecewise function. Piecewise function is where you have different functions, pieces of different functions in one graph. And the book shows Leonardo DiCaprio and Angelina Jolie. What did they do? Relative number of news headlines for popular Hollywood figures over a period of 1 year. So they have both graphs in one. Oh, maybe I should take a picture. You can see piecewise function. What did I do now? Okay, don't show again. That's what happens when it gets late. Here you go. They have both of these graphs in one coordinate system. And you can compare who had more headlines. It was Angelina Jolie. That's probably when, I don't know, when did she get divorced from Brad Pitt? I don't know. I can't remember. I have no idea. Okay, so piecewise function. In one graph, you have more than one function. You have different restrictions on the piecewise function. So let me pick one out of the book. Number 23, why not? F of x is negative 2x if x is less than 0, and x squared if x is greater or equal to 0. So this is the notation of a piecewise function. And in this case, you have two functions. You have a negative 2x, which we all know is a linear function. And we want to graph this function, both function in one coordinate system, but we can only graph the first one, the negative 2x, when x is less than 0, and we can only graph x squared when x is greater than 0. So how do I do this? I make two t-tables, one for negative 2x and the other one for x squared. Now we have restrictions here on the domain. The first one can only be used if x is equal to 0. But in order to graph it, we have to include the restriction, even so it's not actually a point on the graph, and we will represent that with an open circle. So we always start here. Whatever value this number is, that's where we start our graph. included or not, doesn't really matter right now. But we're graphing when x is less than 0. So give me another value that falls into this domain. Less than 0. -1, -2, -3. I mean, 2 would have been enough, but here we are. So I plug it into my function -2x. -2 times 0 is 0. -2 times -1 is 2. -2 times -2 is 4. And +6. Here you go. -1, -2, -3, -4. 1, 2, 3, 4, 5, 6. So can everybody see what I'm doing? I'm using the first function, -2x, and I'm making a t-table for the restriction that is given to us. But I gotta start with the 0. And when I plot this point now, the first point, 0, 0, is not included, so I'm going to have to make an open circle here. -1, 2, -2, 4, and of course we all know this is linear. The first one is a linear function, so it's a straight line that looks like so. And it keeps going, you need an arrow. Guys, are you with me? I know it's late, but this is important. Why, again, do I have an open circle here? 0 is not included. This point is actually not included. Now I'm changing color to blue. And I'm going to graph x squared. And again, I start with 0, and I'm picking 1, 2, and 3. If x is 0, y is 0. 1 squared is still 1, 2 squared is 4, and 3 squared is 9. I'm going to go up here, 7, 8, 9. I'm going to graph this point. And that point, 0, 0 with the x squared function, is that a solid one or an open circle?
Solid.
That one is solid because that's actually included. So I'm going to plot my blue point right in the middle of my red open circle. And then I have 1, 1, 2, 4, and 3, 9. Now you got to know that this is half of a parabola, so you got to have a little bit of curvy action going on here and not make this like a straight line. Oh, and I can use my beautiful parabola template. Here you go. It looks like so. 2 pieces, 2 functions in one graph. Now, what is the domain for this piecewise function? -infinity to +infinity. What is the range? 0 to infinity. What is f of 4? F of 4. Which one do you use? The first function or the second function? For f of 4, it's greater than 0, so that will be 4 squared, that is 16. What else can I ask you? What is f of 0? That's pretty obvious because either way it's 0. So on Thursday, we're going to graph one or more piecewise function. We're done with 2.6. We're going into difference quotients, and then we're moving on to the rest of chapter 2. Okay, have a good evening.